Okay, I'm going to talk about section 5.2, exponential growth and decay. This is not a new topic for you. You folks have dealt with this in past math classes and also probably some science classes. But you're probably just given some formulas with not a lot of explanation as to where they come from or the big idea behind it. So what we're going to find today is that exponential growth and decay always comes from a specific differential equation, which we're going to get into today. This differential equation actually is verbalized right here. So we get an exponential situation whenever the rate of change is proportional to the dependent variable. So let's think about what that's saying. Rate of change is a derivative, okay? Or a dy over dt. I just use dt because with exponential growth, usually the independent variable is time. Y can be all sorts of different things. And if it's directly proportional to our dependent variable y, the output in other words, okay, then what we get is a formula that looks like this. So this is the differential equation that will always spur an exponential model. Okay, so one of the things you saw earlier this week is this discussion of proportional. If I say that something's proportional to something else, that means there's a constant of proportionality, which I'm calling k here, which you multiply by 1 to get the other, and then vice versa, okay? Now, what I'm going to do here, so first of all, let's talk about some examples where this shows up. So this is any time the rate of change is proportional to the dependent variable. So one of the things that you guys know is that when you're investing money, when we look at financial situations, so these are some examples here. You know, the more money I have to invest, the more money I'm going to make, right? So, and that amount that I'm going to make is directly proportional to how much money I have, correct? So, for instance, let's say we're talking about a simple bank account or something like that, where I'm getting a certain amount of interest. You know, let's say the interest is 1%, which is actually, by today's standards, a savings account is quite a lot. So let's say I put $100 in there at 1%, that's going to be $1, right? And if I put $1,000 in, the amount I'm going to get is going to be $10. So the amount I'm going to make, the rate of change, is directly proportional to how much is there. So one is just investing money. The more money invested, the more money I'm going to make, okay? Another one is population growth. And by the way, the population growth only works until we sort of get to a limiting capacity, which we'll talk about. Actually, that comes from a different differential equation, which is not something that we'll talk about in AB, but is something we'll talk about in BC. But population growth, you know, if we're looking at whatever population of wolves or whatever, the more wolves there are to reproduce, the higher that growth is. So very similar to the investing. And then the other one is radioactive decay. You know, when we're talking about half-lives and things like that, the more material there is, there's more decay we're going to have over a particular period of time. So this shows up quite a lot. I will tell you that word exponential gets overused in kind of out there, you know, sort of in the real world. Whenever we talk about exponential growth or whatever, it always is, you know, so you have to look at the situation of what they're talking about. Is the rate of change directly proportional to the dependent variable? Okay, so what we're going to do is we're going to get into calculus here. Okay, so what we're going to start off is by solving this differential equation, the one that gives us an exponential growth or decay. So once again, the rate of change is proportional to the dependent variable. In order to solve this differential equation, now one of the things that we worked on are differential equations that look like this, where we would have like 2t, and then if we solve this, remember when we solve a differential equation, it basically means we're going to get the y equals. These are really easy because they're completely in terms of the dependent variable, excuse me, the independent variable, which is in the denominator. So this would be t squared plus c, and then we're done. And once again, this is what's referred to as the general differential equation. This is not in terms, I can't just integrate this. If your dy over dt is equal to the dependent variable, and I can tell that because that's the one in the numerator of this notation here, or a combination of both, then I can't just simply integrate it in order to solve. I have to use a method called separation of variables, which we're going to be getting into more in the next few sections. So separation of variables basically means this. I'm going to look at this as just a fraction. Y stuff over T stuff, and we have Y stuff over there. So basically the idea of separation of variables is I'm going to get the Y stuff over on this side through multiplication and division, and I'm going to get the T stuff on the other side by multiplication or division. No adding or subtracting. So for instance here, if I divide by Y, I'll end up with dy over Y on this side. And then if I multiply both sides by dt, I'll get k dt on that side. So k, once again, is just some constant we don't know. So we're getting the y stuff over here and the t stuff over here. Generally speaking, any constant, ultimately we're going to have to solve for y. So any constant we typically want to get on the other side, that's usually going to be easier. Now, since I have these separated, y stuff over here, t stuff over here, I can integrate both sides, okay? This is going to be 1 over y. The antiderivative of 1 over y is ln, absolute value of y. I'm going to go ahead and start off by putting an arbitrary constant on this side. I'm going to call it c sub 1, because over here I'm going to have c sub 2. So the antiderivative of any constant will be k, and then the dependent or independent variable t, and we'll have another arbitrary constant. Now I just want to show this to you. What I want you to understand is c sub 1 and c sub 2 are both arbitrary constants. Those are sort of, they kind of morph until we plug in an initial value. So what we're going to do now is we're going to solve for y. Now the first thing we can think of is subtracting both sides by c sub 1. This is really not necessary, because what I'm going to end up getting is another arbitrary constant on the other side. I'm going to get kt plus c sub 2 minus c sub 1. Well, this is still an arbitrary constant. Okay, so in general, moving forward, when we go through this process, we don't have to do an arbitrary constant on both sides, just on one side, and since we're ultimately going to have to solve for y, generally put this on the other side. So we could have gone right from there to ln, absolute value of y is equal to kt plus c. Okay, and this c sort of, and we'll see more of this does get a little confusing here. Now we have to solve for y. So keep in mind, this is in log form. I'm going to want to write that in exponential form. So it's going to be the base here to this is going to be my exponent of absolute value of y. So if I write this in exponential, it's going to look like this. Absolute value of y is equal to e to the kt plus c. Now the last thing in order to solve, okay, is that let's think if I give you the absolute value of x equals 8, what does that mean? It means x could be negative 8, it also could be positive 8. So the way I can get rid of any absolute value is I can put plus or minus on the other side, as long as we don't have any extraneous solutions, like if this was negative 8 or something like that, then there'd be no solution. So I'm going to get y is equal to plus or minus e to the kt plus c. Now let me point out that this is actually solved now. This is a general solution. However, this is probably not a formula you've noticed when you've worked with investing and things like that in past classes. So we have to do a little bit of simplification here. That's a little bit strange. The first thing to realize is if I have something like x squared times x to the third, right? When I multiply things with like bases, I end up adding the exponents. It ends up being 2 plus 3, or x to the fifth. What we're actually going to do here is we're going to do the opposite. When we see something like 5 to the a plus b, I can actually go the opposite way. I can call this 5 to the a times 5 to the b, and this is exactly what we're going to do here. So I'm going to get y is equal to plus or minus e to the kt times e to the c. This means the same thing because since they have like bases, I would add those exponents. Okay. Now I can rearrange this because multiplication is commutative and associative and generally plays nice. So I'm going to call this e to the c and then e to the kt here. Okay. Now here's the thing. Once again, this is perfectly solved, but plus or minus e to c is a constant, c is a constant. Plus or minus means it could be positive or negative. Basically, this value here is just some other arbitrary constant, okay? It could actually be any possible value except for 0. If this is 0, then basically the whole thing zeroes out and it's not really exponential anymore anyways. So what I can do is I can rename this C e to the kt. Now I know this seems a little peculiar to you, but that is the way it is. And this is the formula that you might recognize. So I know in earlier math classes they sometimes refer to this as the PERT formula. P being right here, and that is the principal. And then e to the, and then RT, R would be the percentage rate. So this is the formula we're used to, and once again, that comes from this differential equation. Whether you're talking about population growth, radioactive decay, it comes back to this formula. Okay, so this is the formula that we're generally going to be working with today. Now, here we go. So this is something that you've worked on for a long time without really understanding calculus. The big thing in this class is, now that we know how to get there through this calculus process, this is a formula we're going to be using to answer questions that are not necessarily on their face calculus based. But as soon as we talk about exponential, folks, we're talking about calculus. Let's get into some examples. Okay, our first example is a pretty straightforward one. So they say the rate of change of y is proportional to y. So once again, we know right off the bat that that gives us the differential equation dy over dt is equal to k y, y being the constant proportionality. So as soon as I get this, I know, and you don't have to go through this process every time, because we know that this gives us the exponential equation, y is equal to c e to the kt. So from here, because we've worked with this formula in past classes, from here really, that's it for the calculus. The calculus part of these questions is just recognizing when they say the rate of change or the derivative is proportional to the dependent variable, the output, we know then we're dealing with an exponential situation. So the difference here is sometimes they'll tell you it's exponential, but a lot of times they won't. They'll just tell you this and you have to recognize that that is indeed exponential. So from here, this is actually a pretty easy one. One thing that I didn't talk about before, but the thing to realize is, so basically we want to come up with an equation here. So in other words, we're going to work on solving C and solving K, and that way we can find this at t equals 5. So the first thing we want to do is find this formula. Okay, we're given 2 points here, and this is pretty common. The fact they give me the 0 here makes this quite easy, which I'll talk about in a second. This 0, what we would call the initial value, is basically, you know, anytime we have the initial value 0, y sub 0 being the y value at 0. For this formula, it always works out the same way. So if we take this point and plug it in, so in other words, we're going to plug this in for t and y sub 0 for y. Think of y sub 0 as being some value, like here it's going to be 3. This will be c e to the k times 0. Now k times 0, of course, is 0. E to the 0 power, anything to the 0 power other than 0 is 1. So we get y sub 0 is equal to c times 1. So we get c is equal to y sub 0. So what that means is the y is always, the c is always that initial y value or output value, the value at time equals 0. So as soon as they tell me this, right, I know that c is equal to 3. So right now I have the formula y is equal to 3e to the kt. Now all I have to do is solve for k. So now I'm going to take this point and I'm going to plug this in. Now one caution here, we really don't want to use our calculator till the very end. So we're going to manipulate this algebraically. So this will be e to the, and we're going to plug 1 in for t, so that will just be k. And I'll show it there. So k times 1. All right, so then what I get is, let's go ahead and divide by 3. We get 4 is equal to e to the k. So now how do I get that k down? Well, all I'm going to do is go from exponential formula to a log formula, and we're going to do log base e. So that means that we're going to have k is equal to ln of 4, right? Because the question is, what do I raise e to get 4? So that's e to the k is equal to 4. Okay, so we definitely want to know how to manipulate from log to exponential and vice versa. All right, so this is our k. Like I said, I do not want to solve it. I want to leave it in that form. So now I have my exponential formula. So y is equal to 3 e to the ln of 4 times t, and this is my exponential model. Now all I have to do to figure out what this is, I'm going to plug 5 into that. So y of 5 is equal to 3 e to the ln of 4 times 5. So let's plug that into our calculator, and what we get is 3,072. Okay, so once again, the only calculus was recognizing this. Let's go ahead and we will go ahead and do some more examples. Okay, example 2, an insect population increases according to the law of exponential growth. There were 250 insects after the 3rd day and 400 insects after the 4th day. How many insects were in the original population? So this is actually, we know it's exponential growth, so we know it's going to be something of this form, y equals c e to the kt. But there's really no calculus here. They didn't tell us, they give us a differential equation. So really this problem is just about finding c. So once again, when we're trying to model these things, we want to find c and k. Here they just want that initial population. As I talked about in that last example, that c does end up being that initial value for y. In this case, the number of insects. Okay, so what I need is a solve for that. Once again, you want to look for the 2 points. So here we have, there were 250 insects after the 3rd day, and then we had 400 insects after the 4th day. So that we have 2 points, 3, 250, and 400. That's going to allow us to solve for c. So I need to plug both of those in. Because I have 2 unknowns, I need 2 equations. So 250 is equal to c e to the kt, so that'll be 3 times k, all right? And then the other equation is going to be 400 is equal to c e to the, and then 4k. Now, what we have to do here is we have to end up solving for c. So what I'm going to do is I'm going to solve for c here and then plug it into this equation here. That's generally going to be the easier way, which I'll show you in a second. So obviously to get c here, I'm going to divide by e to the 3k. Generally going for the c first, solving for c first, it makes this easier. So what I end up getting is, so this cancels, and what I'm left with is c is equal to this thing. So then what I can do is I can plug this in for the c over here. And we're always going to be able to simplify this term. So we're going to get 250 over e to the 3k, and then we have e to the 4k up here. So I just replace the c with this here. Now notice, we're always going to have the light base because we have e here. So e to the 4k minus e to the, e to the 4k divided by e to the 3k, I'm going to divide those exponents. So 4k minus 3k is just going to give me k. So what I'm left with is, so e to the 3k divided by e to the 4k, we subtract those exponents, we get e to the k. So we're going to get, we're going to solve for k here. So 400 divided by 250 is equal to e to the k. I know I can get that k'd out by using ln of this side, so k is equal to the ln of 400 over 250. Now, I don't want to calculate this. If I did calculate this, I would need to store that because I want to have my final answer accurate to 3 decimal places. So I'm just going to leave it like this. And now to get c, I'm going to use this formula here. So c is equal to 250 over, and then e to the 3k, and this is k. So 3, and then ln of 400 over 250. And let's calculate that. And what we get is C is equal to 61.035 and then 1 insects. Now, if you're sitting here saying we can't have fractional insects, let me explain this. If these problems do show up, real problems show up on the AP test, sometimes they'll ask you to round to the nearest insect. So if that's the case, certainly go 61 insects. If they don't say round, then you gotta remember what we're talking about as a model. And to look at a portion of an insect might make sense within the context of a model. So only round unless it's specifically asked you to round in a case like this. Okay, let's do one more example with these types of things. This time we'll do radioactive decay. Okay, example 3. How long will it take for 12 grams of radioactive material with a half-life of 1,599 years to decay to 1 gram? So once again, on its face, it's not a calculus problem. We just know that the mechanics behind this are all about calculus. So radioactive decay, let's talk, or any decay, or any time we have a exponential decay instead of growth. So you're still dealing with the rate of change of y being the amount of material you have, of ky. So you still have this differential equation. It's just that k is going to be negative because the rate of growth is negative. It is decreasing. So as y decreases, so does dy over dt. So dy over dt is negative. It's decreasing, right? So we still end up with the formula y is equal to c e to the kt. That doesn't change. We just know ultimately we're going to get a value that is positive. Now this half-life thing, that takes a little bit of work here. Realize what that means is how long will it take for the material to drop in half, whatever that material is. So the way we figure this out, that means that our output would be 2 if our initial value was 1. So that, like if c is equal 1, how long would it take for the output to be 2? And oh, it's the other way around, my bad. I'm thinking of doubling our money. So we're going from 2 to 1. How long will that take to drop in half? Regardless of how much material is, that's how long it'll take. So this will be e to the k times t, which is 1,599. So we can solve k fairly easily here. So once again, I don't want to do any simplifying until the end. So this will be 1/2 is equal to e to the 1,599k. And now I'm going to do 1,599k is equal to ln of 1/2. So what we get is k is equal to ln of 1/2 over 1,599. Now, if you've worked with half-life in a science class, you probably were given a formula that wasn't quite like this. It was probably negative ln of 2 divided by the half-life, or something of that nature. In calculus, we want to be able to work with the formulas. We're not going to be given a formula that we just memorized. If you did memorize it, that would be fine, but you know, my feeling is keep your memorization to a minimum. So now this is our k. So in order to get when it's going to drop to 1 gram, I still have to find c. So I'm going to plug this in here. So we've got y is equal to c e to the k. So that's ln of 1/2 divided by 1,599, and that is t. And once again, this is a negative because of the ln of 1/2. So don't be thrown off by that. Like I said, the decay is going to give us a k that's negative. All right, so now we need to find c, and that's where, how long will it take for 12 grams of radioactive material with a half-life to decay to 1 gram? Oh, we know what c is. My bad. Sorry about that. We know what c is. C is 12, right? So it starts with 12, and so this is our formula. We want to know what the t is to have this drop to 1 gram. I apologize for that. Remember, c, you know, they don't necessarily say it's in the formula. There's always that initial y value, that initial output. So e to the k, so that's ln of 1/2 over 1,599 is equal to t. So to solve this, first of all, I want to divide that on your side, so we get 1/12 is equal to e to the k. And now to get this down, we're going to ln. So this will be, we have our k. And if you get sick of writing this, this can be a little tedious. Feel free to calculate this. Just make sure you store this on your calculator. So this is going to be equal to ln, actually I've lost my t, ln of 1/12. So t is equal to ln of 1/12 divided by, and then our k, which is, I should have stored this. It would have been easier for sure. Oh well. Anyways, so let's go ahead and calculate this. So ln of 1 divided by 12. I haven't made videos in a while. I'm kind of out of practice, I think. Okay, and then we're going to divide it by our k here, which is ln of 1/2 divided by 1,599. And what we get is 5,732.355 years. Once again, go ahead and just leave that as a decimal, accurate to 3 decimal places, unless they say something like round to the nearest year. All right, we have one more example, and that will be it for this video. Okay, example 4, solve the differential equation y prime equals 4x times the quantity 2 plus y. We're back to calculus. The other 3 examples really weren't calculus. You could have done those just knowing the formulas. The difference here is now we understand the relationship to, hopefully you understand the relationship to differential equations. So here we're back to the calculus. Now, first of all, when they give us this notation, I want to write y prime in terms of the y and x, because I want to separate those variables. So this will be dy over dx is equal to 4x times the quantity 2 plus y. So here's the thing, if I separate variables here, you can't add and subtract. So I wouldn't want to do something like distribute the 4x so that then I would subtract something. You can't do that. It has to be through multiplication and division. Keep that in mind. Only multiplication and division in whole quantities. So what I'm going to have to do is I'm going to have to divide both sides by this whole quantity here. So I'm going to get dy over 2 plus y. That I have to divide both sides by this, and then 4x dx. That is how I separate the variables here. Notice I kept the 4 on this side. That really is typically going to be the easiest, because ultimately I need to solve for y over here. So now once I separate those, I'm going to integrate both sides. Well, realize this is a base of, or degree 1, so this is going to be ln, absolute value of 2 plus y. Keep in mind, we only get the ln if this thing is a degree 1 in the denominator. If it's a degree 2 or anything like that, we're going to call that, to the negative second and then do it from there. The antiderivative of 4x is 2x squared. And then keep in mind, when we do these, you only need a c on this side, the side opposite of the y. So we do have to solve for the y here. So I'm going to write this in exponential. So this is going to be the absolute value of 2 plus y is equal to e to the 2x squared plus c. Now, a couple things, and this relates to what we talked about with the differential equation. First of all, we can get rid of the absolute value by putting a plus or minus on this side. And I'm going to go through this process one more time here. I will tell you, it'll get to the point where you just go through this, you just do this process, you don't show it step by step. Now this, I can write as, once again, step by step here. This is going to be plus or minus e to the c, because I'm calling this e to the 2x squared times e to the c. All right, so the e to the c I'm moving out front, e to the 2x squared. And then this is just another arbitrary constant. By the way, we can do this sort of morphing of the C. If you add, subtract, multiply, or divide anything to the C, you can just call it C. You don't have to call it 4C or anything like that. However, C, people get confused with this. So C has this ability to sort of absorb operations that you do to it, but it does have to follow the general rules, the mechanical rules of algebra. And we'll see some examples that sort of show us that, but right now we don't have to worry too much about this. So this is just going to be C. All right, so we'll call this 2 plus y is equal to c e to the 2x squared. And then now all I have to do to get y is subtract 2 to both sides. So I get y is equal to c e to 2x squared, and then that's minus 2. So notice this is very similar to the differential, the standard exponential equation, but it's a little bit different. This is something that comes up when we do like the cooling laws and things like that, but we don't have to worry too much about that right now. Now once again, this is what's referred to as the general solution. Okay, getting into later sections, we're going to be solving for C. Once I give you a point, we can solve for C, finding the solution particular to that point. Okay, so that is section 5.2, exponential growth and decay. A lot of non-calculus, but keep in mind, the reason why we're doing this is it all comes back to the differential equation where the rate of change is directly proportional to the amount of the output, the dependent variable. Sorry about the video being a little glitchy. I'm getting back in the swing of things. You're going to be seeing more of these videos coming up. So anyways, I'll get better. So that's section 5.2.